There's one last application to take careful note of before we're done with cross products, and that is the bit about orthogonal vectors. So recall that the definition of the cross product states that the product vector is perpendicular and therefore orthogonal to both of the vector factors. So let me remind you back here of the definition. So we have this definition. You'll notice U cross V is perpendicular to both U and V. And we saw this when we looked at torque. So if I can find myself my wrench picture, hold on. We've covered a lot of notes. There they are. Okay, so when you look at torque, you have a radius vector here. You have a force vector here, right? So you're pushing along this wrench, and the wrench is moving and twisting, right? And the torque goes that way. So if you will, here, the wrench is here, the force is here, it's flat. Right? I'm just pushing this way. And when I do that, that torque will go down through my paper, even without me wanting to. So the radius and the force vector form a plane, right? Two vectors form a plane. But that third vector, the torque vector, the cross product vector, actually goes down through or up, depending on the right-hand rule. But it would be orthogonal either way. So when I have my bolt in my wrench, I know you thought you'd never see it again, but there you go. So my radius is flat. My force is flat because you're pushing, right? So the only force that goes to working towards this twisting power is the force that I'm pushing against. My torque is going either straight down or straight up. And both of those are orthogonal because they're poking straight out of this bolt. They are orthogonal to the wrench and orthogonal to my force vector that I'm applying to it. Because the force vector and the wrench are forming a plane and the torque is going up or down. Interesting. So that means that if they ask you to find an orthogonal vector, you just need to find the cross product, because the cross product would be automatically orthogonal to both the vectors. That's kind of what the cross product does, right? The torque is always perpendicular to both the force and to the radius vectors. So let me make a little note. For example, right, the right-hand rule says that torque, which is your tau vector, is orthogonal to both the radius vector and your force vector, right? It has to be. Okay, so if they ask you to find two unit vectors orthogonal to the vectors A and B, okay, well, I can find an orthogonal vector real fast. All I would need to do is find the cross product, and I've got an orthogonal vector. And then to make it a unit vector, I would just have to divide by the magnitude, right? So first thing we're going to do is find an orthogonal vector. So find orthogonal vector, right? And that will automatically happen when I find A crossed with B, right? A crossed with B will be orthogonal. All right, so I'm going to call that vector V, for example. All right, so let's find a cross product. So I, J, K. A is 2, -5, 0. B is 3, 3, -4. And then there's just a little trick to add on to your matrix, well, the determinant of your matrix. This is 2, -5. This is 3 and 3. And yet again, we do the diagonals again. So 20, 0, and 6. So it's 20i plus 0j plus 6k minus, and then I'll go the opposite direction, -15k, 0i, and then -8j. Which would get me a vector of, let's see, here. v is equal to 20, take away 0, so 20, 0 minus a negative 8, so that's 8. Oh, I'm doing this in bracket notation, sorry. So just 8, comma, and then 6, take away a negative 15, so that would be 21. There's vector v. That's a vector that's orthogonal, right? So v is orthogonal to A, v is orthogonal to B. So note. But the problem is it's not a unit vector, unfortunately. So that's okay. To make a unit vector, I just need the magnitude, right? And then I can divide by the magnitude and I'll be done. So let's find the magnitude of v. So the magnitude of v is equal to the square root of 20 squared plus 8 squared plus 21 squared, which would be the square root of 905. All right, well, how does that help? Well, to make your unit vectors, all you have to do is divide, right, unit vectors in the v direction. You would take 20, 8, and 21, and you divide them by the square root of 905. That will get you one of them. And then, of course, the other one to go would just go in the opposite direction. So then you'd use negative UV. So this would be 20 over the square root of 905. Yes, it might reduce, but I don't care. 8 over the square root of 905. And 21 over the square root of 905. To get another one, so that's one the unit vector they asked for. It's a unit vector that's orthogonal to A and B. So it's parallel to V, but it's smaller because I divided by the magnitude of V. But the second one, so this is the first unit vector, the second one will just go in the opposite direction. So the second one would be negative UV, which would be, here, I've run out of space, so I'm going to hide my page number. So it'll be negative 20 over the square root of 905. Negative 8 over the square root of 905. Oop, man, I got weird there. And then negative 21 over the square root of 905. That's 2 unit vectors. Oh, my 21 looks like a 4. I'm sorry about that. Here, let me erase that. Negative 21. There you go. There's your second unit vector. That is orthogonal to A and B. And so is this one. And you're done.